Dear students, this is our 41st lecture on named reactions, and today's topic is Steven's rearrangement. Steven's rearrangement basically is a base catalyzed 1,2 migration of quaternary ammonium salts or sulfonium salts to the respective tertiary amines or sulfides. So here what happens is basically one of the groups present on either nitrogen or sulfur, they undergo migration in the presence of base to the adjacent carbon. That is why this is called as 1,2 migration of one of the groups on nitrogen or sulfur. The original reaction which was reported in 1928, that was by Thomas S. Stevens, and in this reaction what happened was that when he treated one phenyl to N dimethylaminoethanol and benzyl bromide, then the corresponding quaternary ammonium salts of this type was formed. And in this quaternary ammonium salt, you can see that one of the group is benzyl group, other two groups they are methyl group, which are present on the quaternary nitrogen. And when this quaternary ammonium salt was reacted with the base, in the present case he chose sodium hydroxide in water, so we can say aqueous sodium hydroxide. When it was reacted with this ammonium salt, then 1,2 migration of this benzyl group from nitrogen to carbon took place, and the product formed was this type of tertiary amine. So such a migration or rearrangement reaction was called as Steven's rearrangement because of the name of the scientist who has discovered this in 1928. Now, as far as the mechanism of this rearrangement is concerned, this is one of the most controversial mechanisms in organic chemistry. And basically, there are two types of mechanisms which have been proposed. We know that bases in presence of quaternary ammonium salts, they will abstract the alpha proton present on the quaternary ammonium salts because of the inductive effect of this positively charged nitrogen. This carbon will have protons which will be acidic and they can be easily removed by the base, and this will lead to the formation of this type of carbanion is formed, where adjacent to this negative charge we are having a positively charged nitrogen atom. So you can say that we will get nitrogen ylides as the intermediate, and these nitrogen ylides then either through diradical mechanism or through cationic anionic intermediate, they are converted into these types of tertiary amines, wherein one of the groups present on the nitrogen is shifted to the adjacent carbon. And if we see the symmetrical mechanism, then the mode of reaction in this case is antifacial. And if we see as per Woodward-Hoffmann rules, then this is a symmetry forbidden process. Therefore, the mechanism which has been accepted is that the quaternary ammonium salts By abstraction of proton, they undergo homolytic cleavage of the nitrogen-carbon bond wherein 1,2 shift will take place. And for example, if we are having say this type of quaternary ammonium salt where one of the carbon is optically active carbon, then by removal of the proton at the alpha carbon to this nitrogen, this will lead to the formation of this type of nitrogen unit. And because of this, we can see that this is a cation anion intermediate which is formed. So similarly, either this can transform into the products through cation anion intermediate or through diradical mechanism. So when homolytic cleavage of this nitrogen carbon double bond will take place, that means this bond will break over here with one electron going to the carbon and one electron going to the nitrogen. And because of the presence of this negatively charged oxygen, the presence of this electron will be all over this part of the intermediate. So basically we will get a diradical intermediate formed, and then combination of this diradical intermediate can take place to give us diastereomeric tertiaramines as the product. So this is how the formation of different types of products in Steven's rearrangement can be explained through homolytic cleavage forming a diradical intermediate. Then there are many applications of Steven's rearrangement. One common application is the Steven rearrangement of these types of benzyl substituted quaternary ammonium salts when one paramethoxybenzyl 1-methyl 3,4 diethyl, where this R1 and R and R1 they are ethyl groups. So 3,4 diethyl 1,2,5 tetrahydropyridinium chloride. So this is tetrahydropyridinium chloride. So when this quaternary ammonium salt is reacted with phenyl lithium as the base, so what will happen? This will abstract the alpha proton as we have seen in the previous slides. This base will abstract this proton, phenyl will take up this proton and it will become benzene, and this will form a nitrogen yelled over here with the breaking of this bond. So we are now having a anion cation pair which is formed. Then this anion cation pair can undergo either 1,2 addition or 1,4 addition to give us these three products. 1,2 addition can take place in two ways. One is that this carbanion can attack this nitrogen and this product will be formed, and other is that this carbanion will form this carbon-carbon double bond and this carbon attacks the carbon next to the nitrogen. So that is how you will get this D, that is 1-methyl 2,2-methyl 5-methoxyhexyl 3,4-diethyl 1,2,5 tetrahydropyridine as the product. So this is how the expected three products they are formed through Steven's rearrangement. And ratios and types of the products which are formed during these types of reactions, they will be dependent on the type of parabenzylic substituent which is this one, and the size of substituent on the heterocyclic ring, these ones. So what is this R? For example, in the present case, this is R and R1 both are ethyl. If we vary these, say methyl and R is methyl and R1 is hydrogen, then the ratio of the products formed will be different and type of the products formed will also be different. Or either all the three products can be formed or any two products they can be formed during these types of Steven rearrangements. Then Steven's rearrangement can also be used for the synthesis of alkaloids. For example, if we take this substrate, that is 6,7-dimethoxy 1,2,3,4 tetrahydroisoquinoline 1 carbonitrile, and we react this with this type of dibromide in the presence of diisopropyl ethylamine in presence of THF, and we reflux these, then they will undergo, with the elimination of HBr, these types of quaternary ammonium salts they are formed. So these spirocyclic ammonium salts, when they are reacted with the base at even very low temperature, then these will be converted into the tertiamines, and these tertiamines in presence of sodium cyanoborohydride, they will undergo ring expansion with the reaction on this cyanide group to get converted into these types of alkaloid, that is xylopinene will be formed as a racemic mixture. So these types of reactions, so conversion of this into this is again a step which passes through Steven's rearrangement. Then various types of isopavines, they can also be synthesized through Steven's rearrangement. For example, azocenes, uh, these isopavines and azocenes and pavines, all these they are biologically active compounds, and they are related to Down syndrome, Parkinson disease and Alzheimer's disease. So that means these are very important biologically active compounds which can be synthesized through Steven's rearrangement. So when azocene, which is a tertiamine, is reacted with methyl iodide in presence of acetone as solvent, then naturally alkylation of this nitrogen will take place, and this tertiamine will be converted into the quaternary ammonium iodide. Then this quaternary ammonium iodide, when reacted with potassium tertiary which is a strong base, in presence of 1,4-dioxane as the solvent, then this will undergo Steven rearrangement to give us isopavines as the product. And again, 1 to shifting of some alkyl group will take place to give us 1,3-substituted dihydro methanodiaryl azocenes as the product. Similarly, you can see this quaternary ammonium iodide, when reacted with tertiary butoxide, again this will form a carbanion at the alpha carbon, and this carbanion will then attack at this carbanion with the breaking of this carbon nitrogen bond, and you will get these types of tertiamines as product through Steven's rearrangement. So you can see that how important this Steven rearrangement is, that we can synthesize many important tertiamines which are biologically active. Now, as far as mechanism of these reactions is concerned, the product formation can take place through two paths. For example, if we say this azocenium ion, this is a quaternary ammonium salt, you know, when we will react this with base, this is the alpha carbon and this is also the alpha carbon. So that means abstraction of proton can either take place from this carbon or this carbon. So this is say carbon number 7 and this is say carbon number 5. Now the two paths are that when abstraction of proton take place at carbon 7, that means this type of carbon ion will be formed, or this is having nitrogen is having positive charge, this carbon is having negative charge, so that means a nitrogen gelate of this type will be formed. And then when this will form a double bond, that means this bond will break, this carbon nitrogen bond will break, and this will change into this type of ammonium anion. And then this ammonium anion can attack this carbon 7 and this double bond will become single bond and this type of isopavine will be formed. Now because of the less steric hindrance, in this case this path is preferred path in comparison to path B, where what will happen, the carbon ion will be formed at carbon 5 and then this will form a carbon nitrogen double bond and this bond will break with the formation of carbon ion at carbon 7, right? And now when these two methyl groups are at these positions and this carbon ion has to attack this fifth carbon, there is a bond between 7th and 5th and the isopavine formed. Now this will be this type, but because of the steric hindrance of these bigger groups, this type of path is not true, and that is why we will get isopavines in these types of structures. Then the Steven rearrangement of tertiary allylic amines was also studied by some authors. What they found is that homoallylic amines, they were formed from tertiary allylic amines. For example, if we are having these types of allylamines and we react these allylamines with benzene, which are formed from these types of substrates, ortho-trimethylsilyl triplet benzenes, when they are reacted with KF, we will get benzenes, and these benzenes in situ will react with these allylamines. Now, when this allylamine will react with benzene, that means the lone pair present on nitrogen will attack one of the carbon. This is a symmetrical intermediate, and the triple bond will become double bond with the negative charge going on the next carbon to which the nitrogen is attached. So we will get this type of 1,3 dipolar intermediate. Then this 1,3 dipolar intermediate will abstract, this negatively charged ion will abstract proton from the alpha carbon, and this will get neutralized and this will have a negative charge now. So basically 1,3 dipolar intermediate will be converted into a nitrogen gelate, and then the nitrogen gelate will undergo Steven rearrangement to get converted into homoallylic amines. So this is how tertiary allylamines, they are converted into homoallylic amines through Steven's rearrangement. Then similarly, similar to the previous reaction, when N substituted cyclic Allyl amines, they were reacted under similar conditions, first with benzene and then formation of 1,3 dipolar intermediate will be formed, and then this 1,3 dipolar intermediate will abstract proton from the alpha carbon to this nitrogen, and this will get converted into a nitrogen gelate. And again in the similar mechanism, this nitrogen gelate through 2,3 sigma tropic Stevens rearrangement will get converted into these types of product, which are N-aryl pyrrolidines. So N substituted like cyclic allylamines through this reaction are converted into N-aryl pyrrolidines. Then another application is that, as you have seen, most of the reactions involving quaternary ammonium salt, similar to this, we can convert beta keto thioethers into functionalized beta keto thioethers. For example, when beta keto thioethers, they are reacted with the benzene, again formed in situ from these types of substrates. Again here also these lone pair present on sulfur will attack this carbon, and this triple bond will be converted into double bond. So that means to one carbon sulfur will get attached and other carbon will have the negative charge. So again we will get 1,3 dipolar sulfides, and then from the next alpha carbon, hydrogen will be abstracted by this carbanion, and we will get these types of sulfurilates. And in a similar manner, what we have seen in case of quaternary ammonium salts, these sulfurilates also, they will undergo 1,2 Stevens rearrangement, and we will get functionalized beta keto thioethers as the product. Then next is double Stevens rearrangement. So when we are having these types of cyclophane derivatives, where you can see we have two sulfide groups present, and when these are reacted with these types of diazo compounds derived from ethyl diisomalonate, and when these disulfides they react, we will get double sulfur gelates, and these double sulfur gelates then they will undergo double Stevens rearrangement to give us these types of products. And this reaction is catalyzed by dirhodium tetraacetate in refluxing benzene. So mechanism of the reaction is same as we have seen in case of quaternary ammonium salts. These are the references which have been used in preparing this lecture. If you want to contact me, this is my mobile number, my email ID, and you can visit our website also at Department of Chemistry, SLIET, Longview. Thank you very much.